All right, we have shown that we can easily solve a system of linear equations. So a system of two linear equations of two variables. So let's say I have this system. So we have some coefficient matrix like this times this column vector, and this is equal to 5 minus 10. So if I have a system of linear equations such as this, right, I can easily solve this for x and y using Cramer's rule, right? Given that the determinant of this coefficient matrix is not equal to 0. So let's say this is matrix A, and the determinant of A is not equal to 0. Then we can apply Cramer's rule to find a solution of this system, right? Now, what if instead we wanted to find the solution more directly by trying to divide both sides by this matrix, right? So for this equation, if I divided both sides by this matrix, could I find a solution directly for x and y? Well, unfortunately, for matrices, we cannot divide by a matrix. Division by a matrix is not defined. So we know that if I have an equation like this, if I divide both sides by 3, I can find a solution for x. I can solve for x, which will give us 3, right? Or we can multiply both sides by the multiplicative inverse of 3, right? And we can also find that this gives us x is equal to 3, right? So what am I doing here? I'm multiplying 3 with this multiplicative inverse. So if I multiply any number by its multiplicative inverse, I will get 1, right? So similar to how we solve this equation here, maybe we can do something here that is similar to, right? We can maybe multiply this coefficient matrix by its inverse in order to find the solution more directly, right? So let's try and take a look into this. So first, let's say that we have a matrix A and a matrix B, and the product of these two matrices, AB, times some vector, some column vector B, is just equal to V, right? And this is for all vectors V, right? So what am I doing here? I'm multiplying V by the composition of these two matrices, right? So what exactly is AB equal to? Well, we know that from previous classes, any vector multiplied by a matrix that is going to give us back that vector unchanged must be just the identity matrix, right? If I multiply any vector by the identity matrix, I will just get that vector back, right? And this matrix here, the identity matrix, this is a unique matrix, right? This is the only matrix that I can multiply the vector with to give me back that vector. So what does that mean? This means that AB must be equal to I, right? And so AB must be equal to this identity matrix. So this is just a matrix where the diagonal entries are 1 and all the other entries are 0, right? So if AB is equal to I, equal to our identity matrix, then we can say that A here, this is the inverse. This is the inverse of B. So A is the inverse matrix of B, right? And B is invertible, right? If AB is equal to I, then A is the inverse of B and B is invertible. This means that B has an inverse. And in this case, the inverse is A. If a matrix is invertible, that means that that matrix can be multiplied by another matrix to get the identity matrix, right? So if a matrix is invertible, then that matrix has an inverse, right? And we can denote the inverse of a matrix. So if I have a matrix B, then the inverse of this matrix is denoted as this, right? And so B inverse times B is equal to my identity matrix. If I have a matrix A, then the inverse is denoted as this, and this will give me the identity matrix, right? So what am I doing here? Just like I multiplied some number by its multiplicative inverse to get 1, I can multiply a matrix A with this inverse to get the identity matrix, right? So in this case, if AB is equal to I and A is the inverse of B, then B is also the inverse of A, right? These two matrices are inverses of each other. Okay, so let's say that we have some matrix M. we have some matrix M, and the entries of this 2 by 2 matrix are these following entries, right? So we have this matrix M, and I now want to find the inverse of this matrix. I want to find the inverse matrix, right? So what can we do? I know that if I multiply M with the inverse, I will get the identity matrix. Let's show this on the left-hand side. I have the matrix M. So the matrix M is 2, 3, 6, 7. Right? Let's say the inverse matrix in general has these entries. So this is M inverse. And if I multiply these two matrices, I will just get the identity matrix. This 2 by 2 identity matrix, right? And this is equal to I. So if I expand the product on the left-hand side, what should I get? Right, I will get a 2 by 2 matrix with the following entry. So I will have 2 times A plus 6 times B. Then I will have 3A plus 7B, 2C plus 6D, 3C plus 7D. And this will be just equal to my identity matrix. Right? So what can I do now? I have a 2 by 2 matrix on the left and a 2 by 2 matrix on the right-hand side. And these two matrices are supposed to be equal. That means we can just equate the corresponding entries, right? So I will have 2A plus 6B to be equal to 1. And then I will have 3A plus 7B to be equal to 0. Right? So now what do we have? We just have a system of two linear equations of two variables. Those two variables being A and B. Right? So let's try and solve this system. Right? There are several ways that we can solve this system. We can use the elimination method, where we can try and get rid of one of the variables to find the other variable, or we can just use substitution. So for this case, let's use substitution. So let's consider the second equation here. So we have 3A plus 7B, this is equal to 0, and I can just find A here. This is equal to minus 7B divided by 3. Right, from this equation, I can find that A is just equal to minus 7B by 3. Now what I can do is I can just substitute this expression of A, that is in terms of B, into the first equation. So I have 2 times minus 7 by 3B plus 6B, which is equal to 1. And this will give me, so we have minus 14 by 3 plus 6B. We have 4 by 3B, which is equal to 1. And from this, we get B to be equal to 3 by 4. So since we have found B, I can now find A, right? I can have A to be equal to minus 7 by 3 times B, right? And this gives me minus 7 by 4. So this is A, and this is B. So we have found A and B, and this is just minus 7 by 4. This is 4. And we have found 3 by 4 to be B. Right? This is the solution of this system. Right? Now, what did we do? We equated, we just considered the first row and the first row of this on both sides. Now we can consider the second row for both sides. We can equate these two entries. So now we will have 2C plus 6D to be equal to 0. And then we have 3C plus 7D to be equal to 1. Now we have this system. Right? So we can use substitution again. We can also use the elimination method. Let's try and eliminate this variable C. Right? Let's try and eliminate C. What I can do is multiply the first equation by 3, multiply the second equation by 2. And we do this so that we have the same coefficients of C. So we will end up with 6C plus 18D, which is equal to 0. And then we will have 6C plus 14D, which is equal to 2. Right, as you can see, we have the same coefficients for C, and I can just subtract these two equations, and I will have 0 here. 18 minus 14, we have 4D equals to minus 2. And from this, I can find that D is just equal to minus half. Right, so this is what D is equal to. Now I can just substitute this value of D back into one of these equations in my system to find C, right? So if I substitute into the first equation, I will have 2C plus 6 times minus half, which is equal to 0. And from this, I see that 2C, so we have plus, this becomes minus 3, so 2C is just equal to 3. And from this, we can find that C is equal to 3 by 2. Right, so we have found D and we have found C. So C and D, this is just equal to 3 by 2 and minus half. So we have found A, B, C, and D, right? So if I go all the way back to the beginning, we showed that the inverse matrix is this, right? So the inverse matrix is just equal to this 2 by 2 matrix with the entries A, B, C, and D. And we have found A, we have found B, we have found C and D, right? What is A? Right, we have A and B here. So this is just equal to minus 7 by 4, and B is 3 by 4. And then we found C and D, right? This is C and D. We have 3 by 2 and minus half. So this is 3 by 2 and minus half. So this is my inverse matrix, right? And you can verify this, right? Our original matrix M was 2, 3, 6, 7. If I multiply this by my inverse matrix by minus 7 by 4, 3 by 4, 3 by 2 minus half, if you work this out, if you find the product of these two matrices, you will see that we just get the identity matrix. So this is M, this is M inverse. These are inverses of each other. Now let's take a look at another example. Let's say we now have some matrix M with these entries, 3, 5, minus 6, minus 10. Right, now does this matrix M have an inverse? Let's try to find the inverse of this matrix. Right, so once again, we consider the inverse matrix to be equal to A, B, C, D, right? And we should know that M inverse times M will just give us the identity matrix, right? So I have A, B, C, D times 3, 5, minus 6, minus 10. This will give us 1, 0, 0, 1. Right, and if I expand the product on the left-hand side, what do I get? I get 3A minus 6B, 5A minus 10B. We have 3C minus 6D, 5C minus 10D. And this is equal to 1, 0, 0, 1. Right, so similar to the previous case, we can find another two systems of linear equations, right? So from the first row, on both sides, I have 3A minus 6B to be equal to 1, and 5A minus 10B to be equal to 0. Right, so very easily I can use substitution here. I can find that A is equal to 10B by 5, which is just 2B. Right, A is equal to 2B. If I substitute this into the first equation, I get 3 times 2B minus 6B, which is equal to 1. Right, so this becomes 6B minus 6B, which is equal to 1. Now, as you can see on the left-hand side, this just becomes 0. Right, 6B minus 6B, we get 0. But on the right-hand side, we have 1. So we end up with this expression, this equality here, right? But this is not a true statement. We cannot have 0 on the left-hand side and 1 on the right-hand side, right? So in this case, we have no solution, right? This system of linear equations has no solution. So if you remember from the previous videos, if we have no solution, then the graphs of these linear equations will just be two parallel lines like this with no common points, with no intersection, right? So in this case, this is not a true statement, so we have no solution. And as a result, we do not have an inverse matrix. So M inverse does not exist, right? So we do not have an inverse matrix, right? Now, why exactly does this matrix M not have an inverse? Why does M not have an inverse matrix? Let's say that we have some matrix A, and let's say that this is an invertible matrix, right? Meaning this has an inverse matrix, right? So A inverse times A will give you the identity. So A is invertible. Now we know that if I find the product of these two matrices, I will just get the identity matrix, right? So if I find the determinant of A inverse times A, this should just be equal to the determinant of the identity matrix, right? And what is the determinant of the identity matrix? This is just equal to 1 times 1 minus 0, which is just 1, right? So this is just equal to 1. And we also know from previously that if I find the determinant of A times B, this is just equal to determinant of A times the determinant of B, right? So this becomes the determinant of A inverse times the determinant of A, and this is equal to 1, right? So now let's go back to the previous example. Our matrix M, this was 3, 5, minus 6, minus 10, right? This was our M matrix. Now if I find the determinant of M, what should I get? So if I find the determinant of this, what do I have? I have 3 times minus 10 minus 5 times minus 6. This gives me minus 30 plus 30, which is just equal to 0. So the determinant of M is just equal to 0, right? Now if M were to have an inverse, right? If M was invertible, then the determinant of M inverse times M must be equal to 1, right? Or we can say that the determinant of M inverse times the determinant of M is equal to 1. But as we can see, the determinant of M is just equal to 0. If this is 0, this cannot be defined, right? We do not have an inverse matrix, right? We cannot have some inverse matrix such that the determinant of that inverse matrix times 0 will give us 1, right? So M inverse does not exist, right? So in general, if I have a matrix, if I have some matrix A and the determinant of this matrix is 0, then this does not have an inverse, right? A is not going to be invertible in this case.